Greetings and welcome back. So let's keep our eye on the prize. What are we doing? We're in the middle of thinking about the frogs on the island of Sao Tome in the Gulf of Guinea off the west coast of Africa. I posed a puzzle, the puzzle being how do amphibians end up on oceanic islands? We talked about snakes on oceanic islands and, like what hypotheses can one come up with. We're exploring the idea that the frogs actually are transported by currents in the salt water, and we're in the middle of trying to work out the consequences of what I will call a concentration gradient across a membrane. The skin is a membrane and it's semi-permeable, and in particular, we're thinking about water flow as a result of higher salt concentration outside of the frog than on its inside. Okay, and now I'm claiming that in order to pull that off, in order to examine it quantitatively, which is precisely the objective, we actually need to talk about entropy and free energy. So this is our first interlude on entropy in the course, and it will come up again lots of times. And the outline of what I want to do here is primarily to do the calculations, but I do have a little bit of philosophical backdrop. So the first thing I want to say, and I think this is extremely important for people that are thinking about the living world, that are biologists, I want to just remind us that in the year 1800, there was no such thing as a gene. There was no such thing as the electric field. The notion of temperature versus heat was muddled and confused. There certainly was no concept of the Poynting vector or radiation pressure. There was no entropy. And there was no second law of thermodynamics. There was no Carnot cycle. Like all of these are new concepts. And in mechanics, we have the notion of the Lagrangian, we have the Hamiltonian, we have the action. These are all concepts. They're not facts. They're human beings thinking about the world around them and trying to see the unity of phenomena. And so, for our purposes, entropy is going to be the key new concept that we're bringing under the roof now. And the reason for the emergence of this new concept of entropy was that there was this amazing success story that you could say in some ways, let's artificially say it begins with Galileo, and let's say it ends in, I don't know, maybe with Lagrange or something. It's not accurate for me to say it this way, but that's the mechanical worldview, the victory of the mechanical worldview, where we started out with planetary motion and projectiles and falling bodies and pendula and those kinds of things, and they fell within the purview of mechanics, and there was a great success. And then people like Euler came along in ways that I'm going to describe next week when we start talking about field theory, and they said, well, hey, if I imagine that water, flowing water, or the structure of a bridge, if I imagine it as made of a bunch of points, I might be able to instead contemplate it as a continuous medium. And so that led to the emergence of elasticity theory and hydrodynamics, which are field theories that describe the mechanics of continuously distributed objects. Again, a major success, a major generalization of the point mechanics of Newton. It also included rigid bodies like a spinning top or a rotating wheel and that kind of thing. So it's huge successes. But somehow it was clear that there were other categories of phenomena and things that you would measure with a temperature, or you'd experience actually when you get near a fire, that there's this thing. It's not exactly a force. It's not like when somebody pushes on you or when you push on a swing or anything like that, or you throw a ball. And so there was this great effort to try to understand the nature of heat and temperature. And Fourier, I hope I will have a chance to talk about this later, and I think I will. Joseph Fourier, if you read the introductory chapter of his book on the analytical theory of heat, it's very prescient, and it's very intentional. It's prescient in the sense that it starts out actually talking about climate, and it's prescient in the sense that it applies to today. He was thinking about the problems of what makes the flows in the atmosphere and the oceans, and what gives rise to wind and temperature differences and all of those kinds of things. And it was intentional because he said, "Oh, there's this other category of phenomena that doesn't fall with under the roof of mechanics as we know it." And he said, I Fourier want to do for that subject what Newton did for mechanics. And in my opinion, he more or less did pull it off. So physics is going to go beyond mechanics. There's kind of two parallel threads, at least, going on in the 19th century of physics going beyond mechanics. One of them is electricity and magnetism and how they end up bringing light into the fold. And the other is heat and temperature and thermodynamics. So physics goes beyond mechanics. And my outline is that I want to talk about Boltzmann and his microscopic rendering of the idea of entropy, and then Gibbs and his full speed, very forceful and mathematical formulation of what we will call the laws of equilibrium or the second law of thermodynamics. So I already showed this in the previous vignette. We're going to build our analysis around the notion of the entropy. So this is a very interesting equation because on the left-hand side we have this macroscopic quantity. In principle, it's something you can measure. It's a comment about, the molecules, all the molecules in this room, there's a certain entropy associated with that. And on the right-hand side is the logarithm of the number of microstates of the system. And so this is the Boltzmann microscopic definition of entropy. There's a second definition, which some of you might have encountered, which is due to Clausius, in which he tells us about a certain integral where he wants us to integrate the amount of heat that's taken on board at a given temperature, and we integrate over this in some sort of a process. So that's the Clausius definition, and I'm not going to touch on it at all from here on. So what I want to do now is I want to talk about this notion of microstate. I want to figure out, what do I mean by the microstate of a system? So the microstate is the particular realization, the particular instantiation of a given process. If I take lambda-phage DNA and I fluorescently label it and I put it on a surface, it will have some sort of configuration. It's 48,000 base pairs long. It'll take some sort of snaky, weird, coiled up conformation. And every one of those conformations is a different microstate, microscopic state of that system. Probably an easier case to imagine is shown here, where I have a system which I'm imagining a glass of water. So I have a glass of water which I discretize into these little blue boxes. So I make the fiction that the continuously distributed water is actually sitting on a three-dimensional lattice. Let's take the lattice parameter of that lattice to be, for example, 1 nanometer cubed. And then the microstate for a given number of ligands L, so you see that L is the number of ligands here. For a given number of ligands L and a certain number omega of lattice sites, then a given microstate is a given realization of where the little red ligands fit onto the lattice sites. Now, the notation that I use up here, W of L and omega, is telling me that the number of microstates depends on two things. It depends on L, how many ligands I have, and omega, how many lattice points I have to decorate with those ligands. And so the thing I'm going to claim here is that the number of microstates is given by this very beautiful and simple expression, and we will think it through now. So how many choices are there for placement of the first ligand? So I have omega places total, and the placement of the first ligand, I have omega choices. That means I can choose to put the first ligand on any one of the lattice sites. Now, how many placements do I have for the second ligand? Well, the answer is I have omega minus 1 choices. Why? Because one of those choices is now forbidden. I'm not allowed to put two ligands at the same spot, and so there's only omega minus 1 choices left for where I put the second one. And I keep on going like this until I reach the last one. And how many choices do I have for the elfth ligand? Well, I've used up a lot of them at this point. So let's see. If I had a total of 3 ligands, the third ligand would have omega minus 2. So what I'm going to do is I'm going to write omega minus L plus 1. Let's just stare at that for a second and see if it jibes with what we expect. If L is equal to 3, then I have omega minus 3 plus 1, which is omega minus 2, and so on and so forth. So there's this dot, dot, dot. So the total number of ways, the total number of microstates, our first analysis of it, is that it's equal to omega times omega minus 1 times omega minus 2, all the way out to omega minus L plus 1. Of course, I could always rewrite this as omega factorial over omega minus L factorial. The point of the denominator here is that this compensates. If I'm going to write the numerator as omega factorial, I remind you, like 5 factorial is 5 times 4 times 3 times 2 times 1. It goes all the way down to 1. So if I have omega factorial, that's omega, omega minus 1, omega minus 2, all the way to 1. But that's not actually what I want in the numerator. What I want in the numerator is this thing, and this denominator cancels off the, if you want to think of it this way, cancels off the spurious additional terms that we put in. So, you can kind of see what the logic here is. So let's imagine a soccer stadium that has 30,000 seats, and the number of ways of putting the blue person is 30,000, because I can put the blue person at every single choice. Now, if I want to figure out the number of ways of putting the blue and the red person, I have 30,000 choices for the first person, and then 29,999 for the second. And why do I say that? Well, for every time that I put the blue person in a seat, I can put that blue person in 30,000 different seats, and then the red person has 29,999 choices left. And we're going to approximate that as 30,000 squared. We're making a very small error as long as the number of people is much smaller than the number of seats. Now, there's one other nuance about this, and that is that I want the people to actually be indistinguishable. In other words, if you look at this right-hand column, these are all the same microstate if the people are indistinguishable. Like when I'm talking about these red ligands, I can't tell the difference if I switch the red and the blue guys because they're both red. So I look at the picture, and those guys are degenerate, so to speak. So in fact, when it comes to counting, I'm also going to divide by L factorial to eliminate overcounting of the indistinguishable, that's the word I'm going to use, particles. So that's the logic. All right, so with that as our introduction, I could, if I wanted to calculate that, so I'm left with W of L comma omega is equal to omega factorial over L factorial omega minus L factorial. I do want to make the observation, this is an approximation, observation slash approximation. And that is that if L is much, much less than omega, that implies that omega factorial over omega minus L factorial is approximately equal to omega to the L power. And that's what I showed you in this diagram here. So if I have three I have three people in a very dilute number of people in the large 30,000 dimensional thing, the first guy gets to choose 30,000 from 30,000 seats. In reality, the second person can only choose from 29,999, but I'm going to call that 30,000. And then the third person gets to choose from 29,998, but I'm going to call that 30,000. So that's this approximation that we write here. Okay, so in light of all that, now let's just sort of examine the entropy itself. So here I'm giving you three different macrostates on the left-hand side. And macrostate here means concentration. It's a macroscopic variable. It's something that I can invent a device and I can measure. I'm not measuring the individual microstates, but I am measuring the macroscopic configuration in the system, and the single macro variable that I use to describe that is the concentration. In this next column, I show you representative examples of the microstates. And then this diagram is intended to convey to us the number of different ways that the system can be configured given that certain number of ligands. So in the top case, that one's kind of easy to see. The total number of microstates is omega because there's only one ligand, and I can put it on each of the individual omega lattice sites. So in this case, the entropy is Kb log omega. In the second case, I have L2 ligands. In this case, I actually specialized to 6. And now what I have to do is I have to figure out all the ways of distributing those 6 molecules across the omega sites. And I just gave you a scheme for doing that, which is to use this binomial description. And we see that there's a simplification, which is this is approximately equal to omega to the L power, L2, I guess, over L2 factorial. So I can take the log of that, and that will give me the entropy. So what's shown on the right-hand side is the entropy as a function of concentration. So what we see is that as we increase the concentration, we increase the entropy because there's more ways to distribute the particles when I have more ligands, although that is only true up until the halfway point. And then by symmetry, once I cross L is equal to omega over 2, now the number of holes or number of vacancies is the equivalent of what was previously the number of ligands. There's kind of a symmetry here. And so the entropy is going to go back down as I pass through 50% occupancy. So now I want to shift, now that we've got the notion of the entropy in hand, I want to talk about the second law of thermodynamics. And I'm going to celebrate the work of Josiah Willard Gibbs, probably the greatest American scientist, maybe, ever. He was at Yale. I'm always amused to think about his very low H index because we're all worried about measuring people's productivity and all that kind of stuff. And one of the ways we do it nowadays is by people's H index, which is some measure of how many papers that a given person has written that are multiply cited. And I just note that, as a lone researcher, Gibbs wrote, I truly believe it's like 23 papers. But, they're doozies. They had a huge impact. So I don't know. It leaves you wondering, if his H index is 23 and mine is 60, I wouldn't, honestly, no false modesty needed. I mean, I'm a pygmy in the universe of Josiah Willard Gibbs. So somehow there's a flaw in that measure. So at any rate, he wrote this amazing paper, published in the weird place, Transaction of the Kinetic Academy of Sciences. And, you can see over here on the left-hand column that he's got the Clausius definition of entropy in play. But what I wanted to call your attention to was what he calls criteria of equilibrium and stability. And basically, what he says up here in this German from Clausius, the energy of the world is constant. The entropy of the world tends towards a maximum. And what Gibbs did was he turned that the entropy of the world tends towards a maximum. He turned that into mathematics. And I guess as an aside, I wanted to say, there's a mathematics of superlatives. When we use words like biggest, fastest, smallest, least area, this, that, maximal area, maximum perimeter, blah, 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 those words that we use, of course, they're words of common speech, but they're also words that have a mathematical punch. And the reason is, when I hear those words, I always think calculus. So superlative thinking means that you want to set a derivative equal to 0. Why do I say that? Because if I want to minimize, for example, at the top left, you see we have this fun little example of a lifeguard and a swimmer. And let's say that the lifeguard, she sees the swimmer out in the water. And the question is, what path should she take to get to the swimmer the fastest? And everything you need to know comes from one simple observation, which is you can run on the beach faster than you can swim in the water. And so that means that the straight line path, which is the shortest distance to the swimmer, is not the shortest travel time path. The shortest travel time path is a straight line on the beach to some entry point and then going out. And so if our goal is to find the shortest travel time, what we do is we write a formula for the travel time, which depends on time spent on the beach, time spent in the water, and you try to minimize that. And the way we minimize a thing is we find slope 0. So that's what I mean by superlative thinking. And I'm going to end this vignette by talking about equilibrium and the equality of the chemical potential, although we won't use those words, but I want them to start floating around in your head. So what I'm showing you here is that I have this box with a partition. Molecules can go back and forth between the two sides, and we're interested in the terminal privileged state, the equilibrium state, or, if you like, the state of maximum entropy. How do we compute the entropy? We add up the entropy of the left-hand side of the box and the right-hand side of the box. You guys will do this in a homework. And then we examine the sum as a function of the number of particles on the left side. And as you see in the green curve, exactly at the point where the number of particles is equal on the two sides, because we've contrived the situation to have the two volumes on the two sides equal, the entropy will be maximized. So as we go from left to right, the entropy of the right-hand side goes down. Sorry, did I say this right? Number of particles on the left side is 0. That means they're all on the right. So I'm starting on the left-hand side. As I move to the right, more and more particles are going to left. So the entropy on the right side goes down. The entropy on the left side goes up. And at some critical point, which in this case happens to be L/2, the entropy will be maximized because the two sides will have the same number of molecules. So this is what I wanted to say by way of introduction. This is our first interlude on entropy. This prepares us now for thinking about the free energy balance and osmotic pressure, which will be our next vignette.